Hey, AP Calculus, Mr. Ellinger, actually, really quick, I'm just gonna reiterate the left-hand and right-hand sum. I kind of looked ahead to what we have to cover. So the big thing when you're doing these left-hand or right-hand sums, I recommend drawing a picture and then just left sum you're going to use for each region. So for like this region, you're going to use the left-hand y value, and for this region, you're going to use the left-hand y value, and so on. So for each region, you're using the left hand and making rectangles and find the area of the rectangles. And for a right-hand sum, you're going to use, again, you divide it into the same regions in terms of the x's, but it's just which y value you're going to use, because the y value keeps changing. You're going to use the right-hand y value. Sorry, those aren't very straight, but they should be rectangles. And so you'd use the right-hand y value. If you've got a function like you do in this one, you can just plug the x in and figure out what the y is from there. Okay, again, I'm trying to do a really short version of this so people have enough that they can get started with the homework and not have to do too much over the weekend. And we're not going to do this. We would have done this in class. Was the plan is that here's a typical scenario, and it's y equals x squared again from 1 to 3. But one thing we could do to improve our estimate is we could use more regions. Like when we do a right sum, now we're doing these tiny little regions or really skinny regions, but the result is that our error is a lot smaller because you can see that the amount that we're off is really, really tiny. There's more little spaces where we've got a little bit of overestimate, but they're really small, so it would be really close. And I hope you're kind of thinking, oh, the more regions we take, the closer our estimate will be because those areas will be smaller. We just need to take a lot of regions, and I hope you're kind of suspecting there's some calculus coming our way, and there is, and limits. And then left-hand sum, same thing. You could take the left hand, and because these curves have all been increasing curves, where the y values are increasing, left hand has been an underestimate and right hand has been an overestimate. But if the curve was going the other way, then that could be different. And then again, the midpoint sum, the weird thing about the midpoint sum, just to keep in mind, is that you're using not the left-hand y value, not the right-hand y value for the same regions. This still has 10 regions. You're using the midpoint x, you're using that y value. So it's not halfway between the two y's, it's halfway between the two x's. Plug that number in and use that one. If the curve is, sort of gradually changing, like gradually decreasing or gradually increasing, then the midpoint's going to be pretty good. I mean, it'll be curved, so it won't be exactly, it won't be perfect, but it'll be pretty close to the right, to kind of like splitting the difference between the left sum and the right sum. Okay, the last thing I want to mention is just to show you an example of a story problem, and this is an actual AP problem, and I just took part A from it. It says a customer at a gas station is pumping gasoline into a gas tank. It's kind of like the barrels of oil. The rate of flow of gasoline is modeled by a differentiable function f. F of t is measured in gallons per second. So please notice this is kind of like we ran into with antiderivatives. They haven't put a prime on this, but this is a rate function. It's gallons per second. And t is measured in seconds. And then it says the question that they asked, I rewrote it a little bit just to make it a little more straightforward for us, is it said estimate the area under this function from t equals 60 to t equals 135 using a right Riemann sum with 3 subintervals. Okay, what's going on with this? If I'm ever confused about these, I always just draw a quick picture. So, and I'm not going to try to be perfectly to scale here. We got 60, we got 90, we got 120, and then please notice that last region is shorter. This is only 135, but these aren't evenly spaced. That's one difference than what we've seen before. And so it says there's 3 subintervals here, 60 to 90, 90 to 120, 120 to 135. Those are the 3 subintervals. And so at 60, it was at 0.1 gallons per second. At 90, it was faster. It was 0.15. I'm not going to try to make the scale on the left. I'm just drawing this picture to help us understand what's going on. At 120, it was back down to 0.1. And at 135, it was down to 0.05. It went a lot smaller. Okay, so now it says estimate. So there's some curve, and maybe, I don't know, it looks like this, or it looks like something, but I don't know what the curve looks like. They didn't tell me that. And so the area, but the area is just going to be made by dividing up into regions, whatever the curve looks like, and we're doing a right Riemann sum. So the right Riemann sum will be using the right-hand y value. If you want to pause it and do it yourself, if you think you understand, you could right now. If you're like, I'm not sure, I'll show you right now how to do it. Just give you a second to pause if you want to. Okay, we're dividing up into regions, so it's a right Riemann sum. So in each subinterval, I'm using the right-hand y value. So it's this y value for this subinterval, and for the first subinterval, it's that y value. So the answer for this, all I've got to show is that I worked this out. So the width of the first rectangle is 30 times the height, which isn't 0.1, that was this one. It's this right-hand one, it's 0.15 plus, and then 30 times the right-hand y value, which is 0.1, and then 15 times the right-hand y value, which is 0.05. This was a calculator question. You can see it was number 1. So, and I haven't done it yet, so I'm doing it right now. Hope you had a good day. I mean, I'm a little frustrated that we didn't have class because it seemed like we could have. I mean, I'm not questioning the safety decision. I thought we could have done a little learning from home, or something, but I just don't want to fall behind, guys. I don't want us to be in a panic later on. The answer I get is 8.25. And then what does your answer represent? I'm just going to say this orally. Well, first, so this is gallons per second, and this is seconds. So gallons per second times seconds, that stands for gallons. And so from t equals 60, this is what you'd write out, but I'm just going to say it for speed. From t equals 60 seconds to t equals 135 seconds, the Riemann sum estimates the total amount of gallons that were pumped by this driver, by this customer, through the pump. So it's an estimate. It's not the real number. There's some real number of gallons, but we were just making an estimate. But this area under the curve stands for accumulated gallons, and we're basing it on a right Riemann sum that was given in the problem. You'll always be specified. If they ask you to do an approximation, they'll always tell you if they want left or right or midpoint. There's one more, but I decided to cut it for time. And so we'll do it later. I'm just making sure I got everything I want to say there. I think that's it. So what I want to show you is this idea of what a left, right, and midpoint Riemann sum is. That's estimating area under the curve. And then as we saw earlier, you divide it up into partitions, and then you just, depending on the problem, use one of the different y values for each region in order to estimate the area of the rectangle, or in order to find the area of the rectangle that estimates the true area. And then in the beginning, it's just and the area under a rate function stands for the accumulated stuff. So just like in the first part of the year, that when we want to estimate the instantaneous rate of change, we figured out we need the slope of the tangent line. That finds the instantaneous rate of change. So this question we have, there's a graphical interpretation, slope of the tangent line. Now we're working backwards, and so it's the area under a rate function, that stands for how much of that thing that we're measuring with the rate function that we've accumulated. Hope that all makes sense. You're just going to be using these things. This will give us, make it so that we can, in the next class, we'll be able to move forward from here. This should cover the basics. Okay, that's it. Good luck. Oh, and I should say, this will be included in the next assignment, so you can do it now, or you could be and then you'll be able to do it later. Okay, bye.